So, let us proceed with the simplest possible example, which is a 1D example. Okay. So, what I am going to do is, for my 1D example, I am going to take a string, okay, and this string is tied at 2 points, x equal to 0 and x is equal to L. Okay. So, that is my string. It is constrained, it is tied at 2 ends and it can oscillate in between anyhow. Okay. So, back from class 12, you used to solve these kinds of equations, the tension on the string and calculate the displacement, all of those things. Lots of constants are there, we will absorb all of those into this differential equation, which tells me that second derivative of u. So, what is u? Is the displacement of the string at any position x. Okay. So, string all right, and F is the applied force. All right. So, we need not worry how we got this equation, right. Mechanics has given this equation to us, which is a second order differential equation. Right. You can already see that if I ignore the well, okay, let me not get ahead of myself, let us continue step by step. Okay. At least the setup is clear, string tied at 2 ends. So, that is my differential equation. So, in this case, for example, what will my L operator be? That is all, right. In fact, this is a there is no need for me to write partial derivatives, it is a 1D problem. So, I can write it as total derivatives. Okay. And my phi is u and my f from the previous slide is capital F. Okay. So, 1-to-1 system I have taken. What for this physical problem, what do you think are the boundary conditions? Yeah, it is clamped at 2 ends. So, the boundary conditions are at both ends, the displacement u of 0 should be equal to 0 and u of L should be equal to 0. Okay. So, these are like nails, you can say, and a string is tied at these 2 points. Between this and between, force is applied like this. Okay. At some point on the at any arbitrary point, I am applying some force. Okay. That force need not be at a point, it can be applied throughout, okay, and that is given by f of x. F of x is a function of x, can be non-zero throughout the string. Okay. You could have placed an object on it, so f is distributed, right. So, we do not care what the form of f is. Okay. As motivated in the previous slide, our main objective is find me g, I can tell you everything. Okay. So, now what is the definition of Green's function now that we can use? How will I just define Green's function very simply, like from the last slide? Same thing, right. So, d2 g x prime d x2 is equal to, okay. You will find in some places this is also written as delta of x minus x prime, same thing. Okay. Okay. So, what is the sort of geometry of this physical problem? We are applying, so this is my x axis, at some point x prime over here, I have applied a force, okay. It is at a single point, remember the right hand side is non-zero at only one point, right, it is a delta function. So, at x equal to x prime I have applied some force, right. So, it is like this, that the string has now become bent, okay, due to the application of this force. Okay. This is, I mean, A physical interpretation is strictly difficult in this case because I am applying a very large force at a vanishingly small point. Okay, so to draw a diagram like this is slightly misleading, because what does it mean to show infinite, I mean the value of the delta function is infinity at that point. But it is just a representation to keep in your mind that what is happening is at one point there is a force being applied to the system, and I want to find out the response of the system. That is what we are doing over here. So this response also will follow the same boundary conditions. Okay, that's one assumption that we will make. Okay, that helps us to solve the problem, and you get a consistent system of equations after that. So we can say this such that same boundary condition. So what can I say? G of x equal to same boundary condition. So that will be x equal to 0, x prime is equal to, so that is just g of 0 comma x prime. I will set that equal to 0 because the string is clamped over there, and g of x is equal to L, x prime is equal to g L x prime is equal to 0. Okay, and if you want, we are going to for now just say x not equal to x prime. Okay, just so that we stay clear of this delta function. All right, setup is clear. Next step is solving it. Okay, so we will solve it directly in the spatial domain itself. Okay, any hints on what should be the first step? When you look at this equation over here, what is the difficult part about it is the delta function, right? It is going to act in a way that will present some difficulty. So if I want to solve something, what the first thing I could try to do is to consider the case where the delta function is not present, and that happens when x is not equal to x prime, right? So what we will do is let's solve this when x is not equal to x prime. In that case, this equation over here, it simply becomes, right. So this should be capital G. Okay. So second derivative of a function is 0. I am taking the derivative with respect to which coordinates? Primed or unprimed? Unprimed. Does this have a simple analytical solution? Yes, what is that? Linear function, right? So I can say that this is simply equal to ax plus b, right? So is equal to gx x prime, right? So this situation x not equal to x prime can happen in two possible ways. One is x less than x prime, and the other is x greater than x prime. Okay, so I'll just draw this one. So again over here, this is my x, this is my the length L, this is 0, okay, and some point over here is x prime. Okay, that's the physical situation. Okay, so when I consider x x is less than x prime, what kind of a solution can I write? So g of x comma x prime is equal to, two cases will be there. The first case, in both cases the solution is ax plus b, right? But will these a's and b's be the same on the left and right? Need not be, right? So I will write it as a1x plus b1 and a2x plus b2. Okay, I have stayed clear of x equal to x prime for now. Okay, so no one can argue with this. In both of these cases, I have a homogeneous differential equation which is g double prime equal to 0. Solution is linear, both sides, right? So how many variables does this problem present? How many unknowns are there? 4 unknowns. All right. So let's use the boundary conditions because that will help us to solve this. Already you can tell one thing, that the left hand side over here is a function of x and x prime. Right hand side seems to only be a function of x. So these constants a and b will be functions of x prime. that you can sort of anticipate now itself, right, and that will come from boundary condition. So, the first boundary condition we can apply is at x is equal to 0. So, I will choose equation 1, right, x equal to 0 comes in the first case, right. So, this is the first case, this is the second case. So, what does that tell me? What does it mean? A1 into 0 plus B1 is equal to
0,
which is equal to 0. So, that tells me that I can't say anything about A1, right, A1 into 0 is 0. Right. Next condition happens at x is equal to L, right. So, here I will say that A2L plus B2 is equal to 0, right. So, I can say that B2 is equal to minus A2L. Okay. The other thing is that we physically expect that the string does not break. So, that is equation of continuity, right. So, the equation of continuity will happen at the point at which I have applied the stress, right. Other places anyway it is trivially continuous. So, this happens at x is equal to x prime. So, that implies that, so what do these two equations tell me? So, so B1 is anyway 0. So, what is the left hand side at x prime? What is left hand side at x prime? A1x prime. Yeah, but we are trying to get at continuity. We used x not equal to x prime to derive these over here, but whatever solution I get. So, let us say just to the left of x prime and just to the right of x prime, right, there is a string that is coming, it can't suddenly shoot up, right, it is a string, it can't break. So, these left limit and right limit I am going to set to each other, so that I get a continuous function, basic definition of continuity. So, that is the left hand side, right, this is from case 1, and that should be equal to the right limit. So, right limit is going to give me what? A2 and B2 I can substitute in terms of this. So, this will give me x prime minus L, right. So, that tells me that A2 is equal to A1 x prime minus L, right. So, I started with 4 variables, and how many relations do I have between these 4 variables so far? 3, right. So, I have A, B and C, okay. So, 3 conditions so far, right. Is that enough? Not really, right. I need one more relation because I to complete give full information about the whole problem. What will that 4th condition be? We impose continuity. That continuity, did it directly deal with the differential equation? No, right. I took the form of the solution, I equated it. So, what is the difficult part we have not yet handled? The differential equation at x equal to x prime. So, now we have no choice, now we must face this, right. So, that is what we do next. What is the final trick? Okay. So, I have g double prime is equal to a delta function, right. So, if I integrate the second derivative, what do I get? Integrating second derivative will give me first derivative, obviously. So, if I integrate just intuitively, if I integrate this on both sides, what will I see? The left hand side will give me first derivative, right hand side will give me 1, right. So, that is something that we can use. So, let us integrate, but what should be the region of integration? So, this is my x prime. So, if I integrate at any region, let us say if I integrate from here to here, is there any use? No, right, because I am not going to get any relation, this function is continuous over there, right. But on the other hand, erased everything. On the other hand, if I integrate from here to here, that is when something interesting will happen, right. So, let us integrate now. So, this is my, I am going to integrate from x prime minus epsilon to x prime plus epsilon, okay. This g double prime x prime, okay, dx. Okay, I am integrating over the length of the wire. So, the variable of integration is x itself, and this will become an integral of x prime minus epsilon, x prime plus epsilon, delta of x minus x prime dx, right. So, what does the left hand side give me? It will give me g dash, integral of the second derivative will give me first derivative, right. So, this will give me g dash of x prime evaluated at x minus epsilon and x plus epsilon, and the right hand side gives me 1, right, because I have included the singularity in the integration. Do I know the value of the left hand side? I do know it, right. So, the left hand side is simply going to give me, so g prime, what is g prime in both cases? A1 and A2, right. So, this is for x less than x prime and x greater than x prime, right. So, this will give me A2 minus A1 is equal to 1, right. So, that is my fourth relation that I needed, right. So, I can just simplify this. I will tell you the final expression that I get. I will get A1 is equal to x prime minus L by L, and A2 from here is x prime by L. Okay. So, I have just done the algebra over here using the, I had this relation also over here, relation C. I put it together with this relation D, 2 equations and 2 variables. I can eliminate A1, A2 and get it from here in terms of what is given, right. So, the final solution that I get over here, I can write it again. I will need 2 cases, right, for x less than x prime and x greater than x prime. So, in the first case, this will become A1 is going to come A1 x, right, that is my A1 followed by x, and the next one is going to give me x minus L by L, right. Yeah, so B1 was 0, so I only had A1 times x, right. So, this is my A1 times x. The next the other equation was so B2 was equal to minus A2L, right. So, then what happened was A2 x plus B2 became A2 x minus L, right. So, I substitute, so this is I substitute, right. So, A2 is over here, so this is A2, right. Okay. So, we can say x less than x prime, x greater than x prime, right. So, it was not so difficult. I used the boundary conditions, I used the fact, I used the information of where I have placed the impulse, and I got the response. So, what will I write the final solution? Final solution is u, the displacement, right. I am going to integrate over 0 to L, right, and that is going to be g of x prime, f of x prime, right. This is the solution, where capital F is any applied force now, which is given to me in the problem. Okay. So, I have just applied the whole machinery of impulse responses, given it a new name Green's function, and shown you in a simple 1D example how to calculate the Green's function. Now, in case that your operator over here, this if this operator was something different, then all the calculations will change, but the idea will remain the same. Okay. Right. So, this is your very simple 1D example, right.